Hello guys, welcome to Ramta Solutions. In today's video, we are looking at grade 12 electric circuits. So, we are not going to waste time. We will get straight into it. So, you are in grade 12. You've come across electric circuits, right? Now, let's begin with a revision. So, this is what you have learned in the lower grades. You remember the word definitions to do with voltage, right? You did say that voltage was work done in moving a unit charge between 2 points, all right? So that gave rise to a formula W V equals W over Q, where this W, we should call it potential difference or voltage, whichever you like. All right, this was potential difference, or if you like, you can call it voltage, measured in volts, symbolized by V. Then this W was the work done, measured in joules. This Q was charge, electric charge, measured in coulombs. All right, this is charge measured in coulombs, capital letter C. Then you then defined current. You said current is the rate at which charge moves past a fixed point in a circuit. All right? We did define that this Q is charge. Now this T is time, of course, in seconds. All right? This T is time in seconds. Then you said a resistance is the ratio of potential difference to the current. So this, you said, is the resistance. All right. You said this is the resistance which you measured in ohms. Right? You said this is the resistance which you measure in ohms. All right. You said this is the resistance which we measured in ohms. All right. Now, this is not all. Of course, we also talked about Ohm's law, but before that, you also need to remember Ohm's law, which I have to write down. Okay, I will write Ohm's law because this is a revision. I will write Ohm's law, which we said potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. All right, that was Ohm's law, isn't it? Let me write it down. So this was Ohm's law, and this is what you did in grade 11. Potential difference across a conductor is directly proportional to the current in the conductor, all right, to the current in the conductor at constant temperature. All right, at constant temperature. This is what you said. I know I didn't write the definitions of potential difference of voltage and that of current and resistance. All right, but I will try to give some other definitions as the video proceeds. Again, we also talked about an ohmic resistor. Right, we also talked about an ohmic resistor. So we are in grade 11 now. We talked about an ohmic resistor. So this is a resistor that obeys Ohm's law at constant temperature. Okay. Okay, it is a resistor that obeys Ohm's law at constant temperature. Okay. this is an ohmic resistor. Whether they say ohmic conductor or ohmic resistor, so it's a resistor that obeys Ohm's law at constant temperature. Okay, so basically, this is to say, for this resistor, it is a resistance with a ratio V is to I that is constant at a constant temperature. Okay, so then we also talked about power. I have to give you the definition of power. Okay, so this power, of course, you know it from work, energy, and power, right? This is the rate at which work is done or energy is transferred, right? So let's write it down. The rate at which work is done, the rate at which work is done, or energy, I can squeeze energy here, or energy is transferred, right? Or energy is transferred, right? So this then leads us to a definition. Rate power is the rate at which work is done. So we say power is equal to work done over time. All right. So we are then going to expand this formula a bit. We said, let me go up. We said potential difference, if you recall, we said potential difference is the work done in moving a unit charge between 2 points. Or if you like, you can say it is energy transferred per coulomb of charge. Do you see it? Here is it. Now we will make work subject of the formula. That is to say, we know work equals, or work done equals potential difference times charge, right? So expanding this, we will then say power equals potential difference times charge over time. And from this, we know that current equals charge per unit time. So this then leads us to say power equals VI. Right. So I'm highlighting important formulas that you know. Remember, all of them are important. All of them are important. And this one here is also important. All right. It's the one that you know. But this can also be expanded. When we expand this, we know the resistance of a conductor. We say R equals V over I, which we can further rearrange and say, we can say also I equals V over R, or we can say V equals IR, right? So other forms of power could be given in this way. Other forms of power could be given in this way. We can say, let's start. We said power equals VI. We can also say power equals, let's substitute in place of I, we're going to put V over R. We'll have V squared over R. Or, once again, in place of V, potential difference, we will put IR. Then we'll say power equals current squared times resistance. These are the formulas of power that you know, right? These are the formulas of power that you know, right? So now we have shown you, all these things, right? These were the formulas that you knew. Now, it's also important that we remind you of parallel and series connections, right? Okay. Let me do this. Let me call this item 1. Okay. Now, let's then talk about we're still under revision. So we're now going to, let me call it 1.1. We're going to talk about parallel and series connections. Parallel and series connections. Right? Parallel and series connections. Or parallel and series resistors, it's your choice. So let's talk about let's start with a series, or maybe I should draw a circuit. First things first, let's have a circuit like this. Let's say this is an ammeter, and let's say this is resistor 1. Let's say this is resistor 2, and then let me try to add more cells. Okay, and let's say here is your potential difference. So this is a series combination. Now let's look at a parallel combination. So for a parallel combination, once again I will say this, and then I'm going to say this one here. Then I'm going to say R1, and then I'm going to say R2. Okay, nice. And here I'm going to say potential voltmeter, sorry. Okay, so this figure here is resistors in series, right? These are resistors in series, and these ones here are resistors in parallel. Oops. Resistors in parallel, right? So I'm going to give you a summary of all these. By the way, when you do electric circuits, it's important that you note the direction of current. It'll flow from a positive terminal. As you can see, if current does not split at a node, it is a series combination. Once again, here is it. Current, as you can see now, it splits here. One portion will be going there, one portion will be going there. This then says to you, current is split. Okay, all right. Now, let's talk about them. It's going to be a tabulation. Okay, so let me tabulate the difference between them, series and parallel. Okay, series and parallel. So let's start. For a series connection, okay, for a series connection, what's happening? Current is the same throughout. Okay, let me just write it in words. Current is the same. Current is the same. For a parallel combination, current is divided. I want you to note that current is divided in those parallel resistors. Now let's go to potential difference. Voltage is divided. Voltage is divided. So each and every resistor in series has its own potential difference. Here, voltage is the same for resistors in parallel. Okay, voltage is the same. So, R, I'm going to say R total, which we should say R fix or RS or R effective, will be sum of resistors. Okay, in this case, we had R1 and R2. And if there's more, you add them like that. So for this one here, you will say 1 over, maybe I should say P, 1 over RP for parallel. And here, maybe I should say 1 over R sub S. I think it's better that way. R sub S. So here it will be 1 over R1 plus 1 over R2 and so on. Okay, and so on. So these are the points that you need. Knowing them, you are good to go. Okay, knowing them, you are good to go. All right, knowing them, you are good to go. Now we are done with our revision. Now let's get to the reason we are here. The reason we are here is nth and internal resistance. Now, this is your grade 12 work, nth and internal resistance. Okay, so now we're looking at the nth and the internal resistance. Okay, now let's talk about nth. What is this nth? Is what we call electromotive force. Okay, it's an electromotive force, but what is it? This is the total work done by the battery per unit charge. Okay, or you can say it is the potential difference measured across the battery when no current is flowing. But I'm going to give you the definition. So, one, let me just give you a total here, maybe different ones. So, I'm going to say this one that might be well received at home. It's potential difference measured across the battery when there is no current flowing, because that is very key. Okay. Potential difference across the battery when, or maybe let me say measured across. Okay, when there is no current flowing. When there is no current flowing. Right? When there is no current flowing. Or you can say it is the total energy. It is the total energy per coulomb. Total energy per coulomb. Oops, Coulomb's law. Per coulomb that a battery can supply. Per coulomb charge. Per coulomb charge that a battery can supply. That a battery can supply. I'm going to leave it here. These are the only two definitions I'm going to give, okay? These are the only two definitions I'm going to give. Okay, so it is also, it is the sum of the it is the sum of the load and the lost volt. Okay, it is the sum of the load and the lost volts. So I've already given you an equation here. Okay, I have already given you an equation here. Okay, so I want you to remember there's something that is very key. I said potential difference across the battery when there is no current flowing. Okay, when there is no current flowing, it's important that you remember this. When there is no current flowing, let me increase the size. When there is no current flowing. Okay, perfect. Now let's go to, oh, by the way, I should say this potential difference, let me see, nth, where is it? Okay, symbolized with this letter here. The symbol is epsilon, right? It's this guy here. Okay, symbol is epsilon, and the SI unit is volt, capital V. Okay, so the formula nth of a cell is equal to V load plus V internal. Okay, plus V internal. Okay, plus V internal. So we're going to expand on this shortly. Okay, we're going to expand on this shortly. Okay, so this is how you get your formula of nth that a battery supplies. Okay, so remember, this is nth. I told you this is the voltage when there's no current flowing. Now this V load this V load, it is the potential difference. What is it? It is the, what should we call it? Potential difference across the terminals of a battery when there's current flowing. Okay. Or voltage. It's totally up to you. Say potential difference of voltage. Okay. So potential difference across the terminals when there is current flowing. Across the terminals of a battery when there is a current flowing. When there is a current flowing. Okay. When there is a current flowing. Okay. And I need you to know that it'll always be lower than nth. So this V load is always lower than the nth. Okay. I want you to note this at all times. It is always lower than the nth. Okay. Now remember, it is across the terminals of a battery. So basically, this means it is for all resistors in the circuit. Okay. I'm going to say for it is the sum of all resistors in the circuit. Okay. Sum of potential, or sum of voltage. Potential difference is a long way there. Sum of voltages, or sum of voltages of all resistors in a circuit. Okay. In the external circuit, let me put it like that, in the external circuit, because there's another resistance we're going to talk about in the external circuit. Okay. In the external circuit. Okay. In the external circuit, it is sum of voltages of all resistors across the external circuit. Yeah? Sum of all voltages or in the external circuit. In the external circuit. Okay. Now let's talk about this internal voltage. So this one here is voltage across the internal resistance. Okay. It is voltage across the internal resistance. All right. So it is also known as lost volt. Okay, it is also known as lost volt. Why is that? Because it is not used in the circuit. All right? Because it is not used in the circuit. All right? Because it is not used in the circuit. Okay, so it is called lost volt. Okay, all right. So now you know these things, right? Now you know these things, and we were talking about internal resistance, right? We were talking about internal resistance. We're going to expand more on that formula. We are talking about internal resistance. Perhaps let's talk about it now once again. Internal resistance. Okay, let's now talk about this internal resistance. So in grade 10 and 11, you were ignoring internal resistance. All right? You were ignoring internal resistance. So with this internal resistance, let's now talk about it quickly. internal resistance. I'm also going to give its definition. I should say it's 2.1. So I don't know why I'm saying 2.1. So internal resistance, I must say internal resistance, I'm going to call it small letter r. Okay? Small letter r. Okay. So this internal resistance, first things first, its definition, what is it? This, do you guys know what it is? Anyone who wants to give it a shot? Okay, nobody wants to give it a shot. No worries. So this internal resistance will be to define resistance. Normally we say resistance is opposition to flow of charge, isn't it? So this one, let's just say, hold on. I'm just going to say opposition to flow of charge. But this one, you must be careful. It doesn't end there. It's opposition to flow of charge, but where? Opposition to flow of charge when? Within a battery. Okay? Within a battery. Okay? You guys get it? So internal resistance is opposition to flow of charge within a battery. All right. So now it is not surprising. It is not surprising. Hear me out. It is not surprising that when there is charge flowing, your battery will always heat up, isn't it? It is not surprising that when there is charge flowing, your battery will always be heating up. It is because of this internal resistance. Okay, it is because of this internal resistance. You guys get it? Okay, so what we have done, once again, we are saying, going back to the formula, mth equals V load plus V internal. So the current that's flowing in the circuit is the same current that is flowing in the internal resistor. So it is the same current, all right? It is the same current, all right? Now you can see this internal potential difference or internal voltage is total current multiplied by the internal resistance. This formula can then be simplified further to say it is current as a common factor equals external resistance plus internal resistance. Okay, this is another way of writing your nth formula. Okay, this is another way of writing your nth formula. Are you guys good? Remember, nth is the potential difference across the terminals when there is no current flowing. Okay. All right. So now, if you have V internal, you can manipulate it to get V internal and current flowing in the circuit. You can manipulate it to get your internal resistance, right? You can manipulate it to get your internal resistance, right? So now let's talk about some few things. Now we're going to talk about some few things. And those few things are, it's important to talk about this. How do we perhaps increasing and decreasing external resistance? How does it affect the circuit from this formula? Okay. How does it affect everything? Okay. So let's do this. Okay, we must go to the next page. So, oops. So let's do this. We'll say, so it'll be two parts, and then you're going to draw the voltage versus current. So number 3, increasing and decreasing external resistance. Increasing and decreasing external resistance. Okay, increasing and decreasing external resistance. So let's talk about increasing external resistance. So increasing external resistance. How do we do that? How do we do that? We can do that by adding a resistor in series. All right, by adding a resistor in series. Sorry, by adding a resistor in series, or by removing a resistor in parallel, or by removing a resistor in parallel. All right, by removing a resistor in parallel. So the effect, what will happen? The results when you do this, what will happen? Remember, of course, external resistance is increasing. What's going to happen? Total current will decrease. All right, total current will decrease. All right, total current will decrease. What about if total current will decrease? Internal voltage will also decrease. But what will happen with the load? The load will increase, right? The load will increase. Remember, mth is constant throughout. Internal resistance is also constant. So let me also mention this. This nth, it is constant. I want you to add further information here. Maybe let's add it here. It is constant. Okay, this nth, this nth remains the same throughout. Okay, nth remains the same throughout. Okay, then we also talked about internal resistance. For the kind of resistances or for the kind of circuits that you are dealing with, this is the same throughout. It does not change. Internal resistance does not change for the kind of circuits you're doing. Okay, this one also remains the same. Okay, remains the same. Okay, remains the same. Right. So let's go back now. So when you increase external resistance, that is by adding a resistor in series or by removing a resistor in parallel, the results will be total current will decrease. When total current decreases, V internal will decrease. However, V load will increase. We're going to explore this shortly, how this is happening. I will show you a mathematical explanation. Now, what happens next? Now, let's try decreasing external resistance. Decreasing external resistance. How do you do that? You decrease external resistance by removing a resistor in series, right? Oops. By removing a resistor in series or by adding a resistor in parallel or by adding a resistor in parallel. Let me squeeze it here. Okay. So what are the results? The results of doing this, what did we say? Remember, of course, external resistance is decreasing. When external resistance decreases, total current will increase, right? When total current increases, internal potential difference will also increase. And then what's going to happen with the load? External voltage or external potential difference, which we call V load, will decrease, right? It will decrease. You guys get it? This is the effect of increasing and decreasing external voltage. external resistance. Now let's look at voltage versus current. Okay, voltage versus current. So the voltage versus current, remember we have mth equals V load plus V internal, right? What we can now do is this. We can say V load equals nth minus V internal. If you are wondering how, it's because we just did this. Okay. If you are wondering how, it's because we just did this, right? So we can say, oh, we are talking voltage versus current. There's a graph that we can draw, right? There's a graph that we can draw. So this graph will be, this being V load. Oh boy, come on. This being V load, then this will be nth. Just hold on. We said we can expand internal resistance to be total current multiplied by internal resistance. Now, you remember what I said to you. I said this internal resistance is constant. It remains the same throughout. So now, what if I say to you, this is giving us an indication that we may have Y equals C plus XM. Okay. How is that? XM, I know you know it to be MX. I basically want to align everything here. If you guys can see this, I basically want to align everything here. Right. I want to show you now. Maybe to show it differently, let me put it like this. It's going to be V load equals negative RI, okay, plus M. How is that? I want you to look at this. I want you to look at this. Now, as you look at this, you can see that we are saying, oh, oops. You can see that we are saying, oh, this negative R is the gradient. All right, is the gradient. Remember, we are drawing voltage versus current. So what does it mean? It is negative R will be change in voltage over change in current. Now, let me show you this graph. Shall we? Let's go. So showing you this graph now, we will be drawing this voltage versus current. So this is voltage in V, current in capital A. Then we will have a graph like this. Okay. And this, do not forget 0. This value here, the y-intercept, is mth supplied by the battery. And the slope here, which we call the gradient, right? The gradient, right? The gradient, what is it? It is negative delta V over delta I, right? So this gradient is negative, right? What is this? It is your internal resistance. Okay, it is your internal resistance. Okay, so the gradient of a voltage versus current represents internal resistance. Okay, it represents internal resistance. Of course, it'll appear as a negative, right? It'll appear as a negative. Indeed, it is appearing as a negative because from this formula, we can, from this formula here, we can see that indeed it's a negative slope, right? It's a negative slope. So that value that you're getting there will be negative, and then when you see, it'll be negative. And when you place it here, it'll give you everything that you need. Okay. So that value S is your internal resistance. Okay. Perfect. So this is all that you need. Okay, this is all that you need for your grade 12 electric circuits. But it would be unfair for us to continue without giving you a wet example. So number 4, wet example. Number 4, wet example. So let's try a wet example. So we're going to draw a circuit, and the information will be, let's draw that circuit. 1 2 1 2 1 1. Okay, and then we have here internal resistor, and then let's say here we have voltage V1, and here we have Okay, now let's see. Okay, let's say one like this one. In fact, yeah, this one is better. And then let me also try this one here. I want to try this ammeter here, another resistor here, and then oh, and I should try a switch, and we label it S, and then I should try another resistor here. This resistor is 3 ohms. It has a resistance of 3 ohms. And let's see, this one here has a resistance of 2,4 ohms. 2,4 ohms, whereas this one here is 4 ohms. All right, this one here is 4 ohms. All right, so let's see. Maybe let me just leave this one as V. So we will say when switch S is open, V reads 15 volts. Okay, V reads 15 volts. Okay, and when it is closed, it reads 13.5 volts. 13.5 volts. What is what is 1, the nth, 2, current flowing in the circuit, current flowing in the circuit, 3, current flowing at ammeter A, current flowing at ammeter A. Number 4, power dissipated by the 3 ohm resistor. By the 3 ohm resistor. Okay, so these are our questions. These are exam questions. So now let's try to look at the information given. When switch S is open, V reads, when switch S is open, comma, V reads 15 volts. Oh, 15 volts. Open, V reads 15 volts. What is this? When the switch is open, there is no current flowing, right? There is no current flowing. What does that mean? This means this part here is nth. Now, when the switch S is closed, it reads 13.5 volts. What is this? what is this? When the switch is closed, there is current flowing. So what is this? This is V load. All right, this is V load. Now the question is, what is the amp? Our amp is simply 15 volts. Do you remember? Amp is the potential difference when there is no current flowing. It is the potential difference applied by the battery. All right, so the amp is 15 volts. Happy? Great stuff. Now, determine the current flowing in the circuit, or what is the current flowing in the circuit? Oh, this we know. Okay, this we know. We can try it in this way because we try in the solutions. We can try it in this way. We know V load, right? We know V load. We might find R external, right? So let's try that. But before we do that, we said number one, amp equals 15 volts. Number two, we are looking for current flowing in the circuit. Let's get the external resistance first. Okay? So we will begin by finding the parallel combination. What is it? 1 over R1 plus 1 over R2. Okay? So it's 2,4 and 4 ohm. Let's go. So 1 over Rp equals 1 over 2,4 plus 1 over 4. Right? 1 over 2,4 plus 1 over 4. So this says 1 over Rp is equal to 2 over 3, telling us Rp 1 divided by my answer in the calculator, which is basically what was down will go up, what was up will go down, or what was at the top will go to the bottom, and vice versa. So this is 3 over 2. What is 3 over 2? It is 1,5 ohms, isn't it? It is 1,5 ohms. All right. Now, what is R external? Remember, this says it is the sum of the resistances in the circuit. It is this Rp plus that 3 ohm. What is this? 1,5 plus, hold on, was it 3 ohm or 4? Yes, it was this 3 ohm because it is in series with the parallel combination, right? So this is 1,5 plus 3, meaning our R external is 4,5 ohms, right? Is 4,5 ohms, isn't it? Perfect. Now we know V load is equal to total current times R right? External resistance. What is V load? We found it to be 13.5. We don't know what the total current is, but we know external resistance is 4,5. Now, what is 13,5 divided by 4,5? Total current is 3 amperes. Right? Total current is 3 amperes. You see, now we have answered questions. All right. The next question, 3, was the current flowing at ammeter A. So ammeter A is on the parallel combination, right? Is on the parallel combination. We know that voltage here, voltage on the 2.4 resistor and on this 4 ohm resistor is the same, right? So let me show you. To get that, I can say, number 3, I will say current at that 4 ohm resistor, let me call it current at the 4 ohm, multiplied by, or let me do it like this, voltage at the 4 ohm resistor is equal to voltage of the parallel combination. Okay, so voltage here of the 4 ohm could be represented by current flowing at the ammeter A multiplied by resistance of the 4 ohm resistor equals current flowing on the parallel combination is the total current multiplied by Rp. Okay, now this we know, we are okay, Right, let's go now. Current flowing is unknown. 4 ohm resistor resistance is 4. Right? We said total current is 3. We said RP is 1,5 if I recall. R sub P is 1,5. Right? Now, easy peasy, our total current is 4,5 divided by 4. That says to us current flowing at ammeter A, or current registered by ammeter A, is 1,125 amperes. Do you guys see how I did this? Okay, perfect. So the current flowing at ammeter A is 1,125 amperes. Now the last question, I believe. Oh, did I skip? I think I skipped a question. Oh, I didn't. Okay, I'm gonna add a question. May I add question 5 here and say calculate internal resistance? Okay, calculate internal resistance R. Okay. Oh no, what is? Because it has always been what is. So this will be what is the internal resistance R. Okay. So we are done with current flowing at ammeter A. Now, power dissipated by the 3 ohm resistor. We know the equations of power. These are given. Power equals VI, or power equals V square over R, or power equals I square R. We do not have voltage of the 3 ohm resistor, so we cannot use these two. We can only use this because we know the current flowing. So we'll say power equals I square, and by the way, power at the 3 ohm equals I square R, right? So what is this? The current flowing there is the total current, which was 3 amperes. And the total, rather, resistance of that resistor is 3. This then tells us, obviously, 3 cubed is 27 watts. That is the power dissipated by that resistor. Now I have added a fifth question that says calculate the internal resistance. All right, easy peasy. But I'm gonna show you now what we have. Let's go now. Number 5, the internal resistance. We know nth equals V load plus V internal, right? We said nth is 15 volts. We said V load is 13,5 volts. And then what is V internal? It's unknown, but we can say it is IR. So this is 15 equals 13,5 plus 3R. 15 minus 13,5 equals 3R. When you look at this, then you will say this looks like 1,5. 1,5 equals 3R. Therefore, internal resistance is, what is it? Is 0,5 ohms. Right? Internal resistance is 0,5 ohms. You can also just get V internal first and say IR, whichever you like. Okay? There is nothing wrong if you say V internal equals M minus V load and say 15 minus 13,5 and say this is 1,5. Then proceed to say V internal equals IR and say 1,5 equals 3R, right? And then R equals 0,5 amperes. It doesn't matter as long as you get it. So this is it, guys. This is how you attempt your grade 12 electric circuits questions. By the way, this example is coming from one of your past papers. Okay, so with that being said, it's a wrap. See you next time. Bye bye.